Example 2 is going to be very similar to example 1. If you'll notice, all I changed was that it's y prime minus y instead of y prime plus y, and I added an x in front of the y squared. So we still have a Bernoulli equation, and our process remains the same. Our first step is we're going to find the homogeneous solution to the linear equation. So if we look at our given ODE, we have y prime minus y equals 0. So our integrating factor, mu of x, would be e to the integral of the function of x that's in front of y, which is just negative 1. So it would just be negative 1 dx, or e to the negative x. When we multiply the entire equation by e to the negative x, we get e to the negative x y prime minus e to the negative x y equals 0. And when we do the reverse product rule, we find that this all came from an e to the negative xy when we took its derivative. It equals 0, so we integrate both sides with respect to x, and we find that we have e to the negative xy equals a constant. So y equals c e to the x when we move the e to the x to the other side by either multiplying both sides by e to the x or dividing through by e to the negative x. And when that e to the negative x ends up in the denominator, we can move it to the numerator with a positive exponent. So we need to find our characteristic solution here, which would be y1 equaling, we'll remove c because that's what we're going to let vary in our variation of parameters. So we're just going to let y1 equal e to the x. And when we move into our variation of parameters step, we're going to say, okay, let's let the full solution be our function of x, u, times that characteristic solution, e to the x. So we have u times y1. So when we find our y prime, our dy dx, we have to use the product rule. So we end up with 1 d2 plus 2 d1. So u e to the x plus e to the x u prime. And now all we have to do is substitute in y prime and y anywhere we find them in our given ODE. And we're doing this in our given ODE as it was written, not in the homogeneous version. So y prime is u e to the x plus e to the x u prime minus y. Well, y is u e to the x, and it equals x times y squared. Well, y is u e to the x, so we'll square the whole thing. So we end up with u e to the x and u e to the x canceling out here. So when we simplify, we find that we have e to the x u prime equals x e to the 2x u. Right? When we do e to the x and we square it, we multiply their exponents because it's an exponent raised to an exponent. And u also becomes squared, so we can't forget the square on the u, and then we have an x multiplied by all of it. So now all we have to do is get all of our u's on the left and our x's on the right. So we would have u to the negative 2 du equaling x e to the 2x over e to the x dx. And when we have two exponentials with the same base and they're divided, we subtract the bottom exponent from the top. So when I do 2x minus x, I end up with just an x. So I end up with u to the negative 2 du equals x e to the x dx. We already know how to integrate u to the negative 2 du. We'll add 1 to the exponent, divide by the exponent. But on the right-hand side, we have x e to the x. The only way we're going to be able to integrate that one is if we end up doing an integration by parts. So let's look at the left-hand side. We'll go ahead and do that. We get u to the negative 1 divided by negative 1, which we could just put out front. So we end up with negative u to the negative 1 equaling, well, now we have to come up with our integration by parts. So let's think about it. If we let u equal x, we know du will just equal dx. So we can get rid of the x that way. And in this, by the same token, we can let dv equal e to the x dx because we already know how to integrate e to the x. We also know how to differentiate it, but differentiating it won't make it go away. And in that case, we end up in a loop and we won't be able to get out of this integration by parts. Our goal is to make sure we can finally get to something we can integrate. So we're going to let v be e to the x. So when we plug in our uv, so x e to the x minus the integral of v e to the x du, which is dx, we now find that we have a function that we can integrate on the right. So now we end up with negative 1 over u equaling x e to the x minus e to the x plus c. From there, all we need to do, multiply both sides by a negative 1, and then invert the fraction. So let me scoot this up a little and make a little bit of room. So we find out then that we've got 1 over u equals e to the x minus x e to the x plus c, because remember, c can absorb a negative, it can absorb a multiplication, there's a lot of things that c can absorb. So when we look at u, we can invert both sides, and then instead of 1 over u, we end up with u equaling 1 over e to the x minus x e to the x plus c. And our last step is to say, well, y is u times e to the x. So we end up with e to the x over e to the x minus x e to the x plus c. So here's the cool part, is that we can either leave it this way, or we can move our e to the x to the bottom, and we can make it 1 over e to the negative x times e to the x minus x e to the x plus c, so that we can simplify our given solution just a little bit more, in that we can end up with 1 over, well, e to the negative x times e to the x will give us e to the negative x plus x, which is e to the 0, which is 1, minus x e to the negative x times e to the x gives us e to the 0 again, which is 1, so x times 1. And then we would have plus c e to the negative x. And that's where we'll finish out this problem.